name is Thomas Martineau, and this is my project design alternatives presentation for ENEL 400. I'm part of Group 7 with Joseph, myself, and Vincent, and our project is a temperature and blood oxygen measurement station. SpO2 just stands for blood oxygen. Now, I thought this would be a useful project for the current times, as you would be able to place this maybe at an entrance to a building or an entrance to a workplace where employees are entering, so they'd be able to self-monitor their temperature and blood oxygen, which are two things that could be used to measure how healthy a person is. So the revised client problem statement for our project is that it needs to be a low-cost system. It needs to be able to measure temperature via a non-contact solution, such as using an infrared sensor. It needs to be able to measure the blood oxygen of the user via surface contact, so putting your finger onto a sensor. The measurements need to be presented to the user through an LCD screen and LEDs. So say if your temperature measures as a fever, it may show up as a red LED and then display your temperature onto the LCD. The SpO2 sensor will be disinfected with a UVC LED between users to make sure that it's safe to use during a pandemic. And the system will communicate over the network and will communicate the number of users that have used the station, if the system is powered on and working, and maybe other user statistics such as if there was somebody that did have a fever, had entered the workplace on a certain day, throughout a certain hour, it'd be able to communicate that to over the network. So here's the block diagram for our system conceptual design. It involves 7 functions: the temperature sensor, the blood oxygen sensor, the user display, the microcontroller, the power source, sanitization process, and a network connection. Everything is kind of focused around the microcontroller, as that's the hub of where everything else connects to. Here's the system design alternatives that we have come up with for our project. The yellow on this chart is what we selected to go with, and how we decided to go with this was by using morphological charts. An example of this morphological charts is on the next slide, which we'll talk about later, but for now I'll talk about all of the design alternatives we had come up with. So for measuring temperature, we came up with 3 ideas. It was to measure the temperature of a user through their hand, through a forehead scan, a stationary forehead scan, or a tracking forehead scan, which would basically track the user's head to know that you're actually aiming at their forehead instead of, say, at a set height. We decided to go with a hand scan. For measuring blood oxygen, we had found just the one sensor that measured blood oxygen basically. To the sanitization process, we had one option of using a UVC LED. For the controller, we had 3 options, which was to use the STM controllers that we've been using in the lab so far throughout our university career, by using a Raspberry Pi, or by using both of them in tandem. We decided to go with both of them. For the user interface, we had 2 options, the first of which was to use an LCD screen and LEDs, or to use a 7-inch digital screen and LEDs. We decided to go with an LCD screen and LEDs. The power source, we had 2 options, first of which was wall power, which is just like your normal plug-in that you would use for your phone charger, or by battery power. We decided to go with wall power. And finally, for the network, we had 2 options of using the network connectivity that's integrated on the Raspberry Pi, or by using an additional Wi-Fi shield for the STM board. We decided to go with the Raspberry Pi. So on this page, we have an example of the morphological chart for the microcontroller option. On the left side of the chart, we have the criteria that we basically used as a rubric on how good a certain option would be. And then to the right of that, we have the different options of the lab board, Raspberry Pi, or both of them. And finally, on the far right, we have the weight or importance of each criteria, which is how important the certain criteria is to the project. On this chart, the higher the number, the better it is. So say for weight, 3 is the highest, and for the score, you'd want to be higher than more than lower. So for cost efficiency, both boards were, or microcontrollers were similarly priced, and then with both of them, it was worse as then you'd have double the cost. For network capability, the lab board was less effective than the Raspberry Pi, as we would need to buy an additional adapter. But both of them together is the same as the Raspberry Pi. For GPIO capability, we found that the lab board and Raspberry Pis had similar levels of connectivity. Both had I2C and display connections. And however, both of them together scored higher due to having double the capability. And for power efficiency, they were both rated around even, with both of them being worse, as together you'd be using double the power. For the weight, we decided that GPIO capability was the most important to ensure that we were able to connect all of our sensors to it. Cost efficiency and network capability were weighted the same, and finally the least efficient, or the least important criteria was power efficiency. The bottom row of the chart shows the total scores, and as I said before, the higher the score, the better. And as you can see, with the Raspberry Pi and both the STM and Raspberry Pi together scored the same, and we ended up going with both of them. Here's a subsystem function overview of the network block. On the left is the block diagram I made for the individual submission. The green block is the actual measurement station itself, which houses the STM board and the Raspberry Pi. On the right is the remote computer that would be on the same network that would be able to communicate with the station. And then finally, the blue, yellow, and red boxes are the three different functions that will be going on through the network. First of which is to send custom messages. So this function would be, say, if it's the holiday time like Christmas and you wanted to display happy holidays on the LCD while nobody's getting a measurement done. So you'd be able to log into the station remotely and be able to send this custom message to be displayed. The next function is to track usage information. So this would be, say, how many users have used the machine, the times of the day that the people have used the machine, or maybe how many users have exceeded a certain temperature or blood oxygen level. This may be too personal for tracking, but we left it in just in case we wanted to actually implement it. Finally, the last function is an "Are you alive?" ping check. This is basically just to check to make sure that the system is actually still powered on and working, and that nobody has stolen it or something of that nature. It's basically just to make sure that the system is still working without having to walk to the actual station, as a company may want to deploy multiple of these around a building. And that brings the end to my project design alternatives presentation. Thanks for listening.